going to go through some of the stuff about air-to-water heat pumps. Really, everyone's talking about heat pumps. We also do a lot of hydronics. There are some key fundamental differences between a high-efficiency gas boiler or electric boiler and an air-to-water heat pump. Let's talk about money. Everyone likes money. Right off the bat, there are rebates available today for air-to-water heat pumps in retrofit applications. Clean BC has rebates available. There are, as of March 2021, 64 qualifying models here in BC that are eligible for rebates. So I know that's a big selling feature for heat pumps. It applies to air-to-water as well. So let's talk about hydronics. What is hydronics? Hydronics is heating with hot water. Hot water is the conveyor belt of heat. Why do we use hydronics? Distribution efficiency, ultimately. When it comes down to it, we can move more heat with water than we can air, and we can move that heat further and more efficiently in smaller spaces. So builders love it. Less bulkheads, smaller pipes delivering the same amount of heat as large ducts. Again, no hydronic radiant floor heating. That's the predominant way we heat here with hydronics. It's a great match to air-to-water heat pumps. It matches human comfort profile. We're talking about warm feet, cool head, optimal human comfort. You heat a bunch of air, it goes up and hangs out on the ceiling. I only know one guy who wrote a song about dancing on the ceiling. Everyone else is down here. We keep the heat where it needs to be. We can be comfortable when the objects in the room are warm, even at a lower air temperature. On top of that, hydronics is flexible. We have all types of different heat emitters. Radiant floor isn't where it ends. We've got radiant walls, radiant ceilings, radiators, fan coils, baseboards, and then other loads like domestic hot water. I'm sure some of you shower, so that's very essential. Then we have snow melt, we have hot tubs, we have pools, all these other fun things we can do with hydronics. So it's very scalable, and we can stage different types of heat sources very well into the same distribution systems, whether that's different fuel types or just multiple appliances to deal with different loads. Radiant floor is virtually silent, very, very popular thing. But I'm not here to sell you on radiant. It's already happening, it's everywhere. But a key difference with air-to-water heat pumps is temperature control. If I can drill one thing home tonight, it's about delivered water temperatures and their effect on capacity and efficiency in a heat pump. We can heat with very low temperatures with radiant floor heating, much lower than anyone would be comfortable if that was the air temperature coming out of a forced air system. So we have an opportunity to deliver very high efficiencies from our equipment because it's such a low temperature heat distribution medium. So there's a quick slide. Some of you guys have probably seen this before. 3/4 inch copper pipe can replace a 14/8 duct undergoing the same temperature change as far as heat transfer capability. We don't think of air as heavy because we're all swimming in it all the time, but it is. We use a lot of energy to move air around. You know, typical house. We're talking 3/4 horsepower blower motor or 1/25 horsepower circulator pump to do the same heat delivery. You know, you take a gas furnace and a gas boiler with the same combustion efficiency, that's neck and neck, but how are we delivering that heat? We can do it much more efficiently with hydronics. And even those 1/25 horsepower circulators are kind of going by the wayside now with modern ECM pumps. So the technology is advancing rapidly. We're a little behind in North America compared to Europe and Asia, so we can look to them for what they're doing. Zoning flexibility. Zoning flexibility is very easy in hydronics. We can put thermostats in every room. I like to remind people, you might have a light switch in every room in your house. Lights do not consume the kind of power that heating and cooling does, so the ability to zone a system to have independent thermostat control in different rooms is very important to saving energy, to comfort, and is very easy to do with hydronics. It is possible with forced air, but a little more difficult. So another advantage for the hydronics guys. We just move pipes around, we have valves, all this kind of stuff. Maybe pop by the hydronic design course when it's ready. We can talk about that stuff. But that's hydronics. What about heat pumps? You guys know what a heat pump is? Pumps heat, as you might think. We're moving thermal energy around. We know that heat goes from hot to cold. So how do we get heat from what's cold into what's hot, like a warm house on a cold day? We just put something colder than the outside air out there, and that's the refrigerant. So we're moving heat from one place to another with a heat pump. We're not creating heat energy like in a fuel burning appliance. We just boil and condense refrigerant over and over. Every time there's a change of state in a fluid, there's a ton of energy change. So we're taking advantage of that, changing its pressure to change its temperature, to change its state, to move heat. Very fun stuff, even more fun with hand gestures. So how does it work? It has a compressor. Compressor compresses vapor refrigerant, changes its pressure and temperature. We move it into something called a condenser, where it goes from a vapor into a liquid as it transfers heat into its medium. And in the case of an air-to-water heat pump, that medium would be hydronics, so water. It goes through a metering device which changes its pressure again, and some other boring stuff happens like an evaporator. An evaporator is where that liquid refrigerant becomes a vapor again and sucks up a bunch of heat. If you want proof of that, put a pot of water on the stove. It starts boiling, it's taking all of that heat from your stove. It's sucking up lots of heat energy. That's what's happening here. So we're just moving heat around. All we do is pay to move that refrigerant around in a big circle. So we've got, in an air-to-water heat pump, two heat exchangers, refrigerant to air, refrigerant to water. So on an air source heat pump, where air is our energy source, that's going to be sitting outside like this large coil on the left side. It's come in all kinds of shapes and sizes, usually copper tubes with aluminum fins. And then inside, we take that refrigerant and transfer heat into water. So that's usually a brazed plate heat exchanger like we've got on the right here. Things come in all kinds of shapes and sizes as well. There's coaxial heat exchangers. Can't cover them all, there's lots of stuff. But nonetheless, we're taking heat from outside air and moving it into hydronic heating inside. Heat of vaporization is important though. When we talk about transferring heat, this is where heat pumps really shine. So who knows what a BTU is? British thermal unit. It's an imperial measurement of heat transfer. So 1 BTU raises 1 pound of water, 1 degree Fahrenheit, 8.33 pounds in a gallon. So we do all our hydronics math with that. But from freezing to boiling in Fahrenheit, 32 to 212, it's going to take 180 BTUs to get from freezing to boiling. To get that boiling water into steam is going to take another 970 BTUs per pound. So we had 180 BTUs per pound from freezing to boiling, but just to turn that boiling water into steam, a massive amount of energy is exchanged. That's what we're harnessing with heat pumps through the refrigerant. So everything going into a heat pump has to be what's coming out of a heat pump. When we measure heat pump efficiencies, we're not talking about percentages of 100% like we do with, say, a gas appliance. We can never get 100% of the potential energy out of that fuel. But in a heat pump, it's always in the positive in percentages. We measure it in COP, or coefficient of performance. So a COP of 1 is 100% efficient. 1 unit of energy consumed delivers 1 same unit of energy. So if we use kilowatts, you buy a kilowatt from hydro and you get a kilowatt of heat, 3,412 BTUs. In a heat pump, we're taking most of that heat from the outside air, which came from the sun, warmed up the air, great stuff. Love the sun, huge fan. The compressor is the thing that we pay to operate. It just moves that heat around. So the heat we deliver is the sum of those two things. The energy going into that compressor and the energy we absorb from the outside air. They're always going to equal each other. So Q1 plus Q2 equals Q3 if you're following the slides. Common, this is not a hard and fast, every heat pump works like this moment, because you're going to see these things are dynamic, but a common analogy would be absorbing 24,000 BTUs from the outside air, using 10,000 BTUs of electrical energy to deliver 34,000 BTUs of heat energy. So we only paid for that 10,000. We got that 24,000 from outside, we delivered 34,000. So that would be 340% efficient, COP at 3.4. Again, not going to be every heat pump in every moment, but one of the advantages of heat pumps and why we see people focusing on heat pumps. We live in a time where the weather is changing, the climate is changing, we're looking for different ways to cut down on emissions. If we can put everything into electric heat sources, we can worry about making that electricity efficient later. Let's just get everything on electric as quick as we can. So reversible heat pumps describe a certain type of heat pump that can heat and cool. Not all heat pumps can heat and cool. So you guys have a heat pump of some kind. It takes heat from inside the fridge and dishes it out behind the fridge or under the fridge. It's just moving heat energy. Air conditioners work the same way. It's the exact same principle. A heat pump just heats the house. Air conditioner cools the house. Reversible heat pump can do both. Use the reversing valve. All the reversing valve does is change the direction of flow after it leaves the compressor. Simple stuff. Not going to get too far into it, but leaves the compressor, goes through the reversing valve, takes a left or a right. Are we heating or are we cooling with that energy? But these are excellent candidates for cooling as well. We don't think of hydronics in cooling a lot, but we can. We can use chilled water to move thermal energy out of a building, and it's, again, high distribution efficiency, just like our radiant floor heating is. It's just hydronics. Instead of heated water, it's chilled water. So we have a few different categories of heat pumps out there you guys may or may not have seen. There's air, there's water. We say it in different orders. Believe it or not, that matters. So I just want to clarify a few things here. There are air source heat pumps and there are water source heat pumps. Air source heat pumps exchange energy with the air. Water source heat pumps exchange energy with water. That's the first word. The second word is how we deliver that heat energy. So we have air-to-air heat pumps, probably the most prevalent we're familiar with. Air source heat pump outside using forced air heat delivery inside. Air to water, the only difference is hydronic heat delivery inside, still air source heat pump. Then we have water to air, not to be confused with air to water. Water to air is a water source heat pump using forced air. And then water to water is a water source heat pump using hydronics to distribute that heat energy. So here's a classic air to water heat pump. In fact, this is kind of vintage. You can't even buy them anymore. This particular product's not on the market anymore, but this is an air source monoblock heat pump. So when we get into air to water heat pumps, we have subcategories. Monoblock is kind of a European name, but it's stuck. It is a packaged unit. So for those HVAC folks in the room, rooftop units, refrigeration's already self-contained. You just hook up some ductwork. Same idea. Hook up some water lines. Heating, cooling comes out. Thing with monoblock heat pumps is if you're a gas fitter plumber, this is probably right up your alley because you're already doing the plumbing side of things. You don't need a refrigeration contractor involved to run line sets, charge it, whatnot. It comes factory charged, ready to go. But we have water lines outside now, and believe it or not, it gets cold everywhere at some point in the year, and that water can freeze. So the key part with any monoblock heat pump is glycol. We're going to have to use glycol in these things to protect them from freezing. Glycol does one thing really well, it doesn't freeze. So you can count on that. But glycol also impacts water flow and pressure drop. So there's some key things to understand about sizing pipes and sizing pumps once you've added glycol. We live in a pretty mild climate here where a lot of people get away with hydronic heating with 100% water. As soon as you run those water lines outside, please, glycol is now your friend. So you might have to educate yourself a little bit on how it works, how to add it, how to verify how much is in there, but key part of any monoblock heat pump. So classic kind of piping diagram, heat pump sits outside the house, water lines come through the building, into the building to where your mechanical room is, and distributed through the building from there. Sometimes people don't like paying for glycol, so they like to isolate a small subsection of the hydronic system to just put glycol in that part and leave 100% water everywhere else. It can be done. You'd use a fluid-to-fluid heat exchanger to do it, but you also have to be careful with that. To transfer heat, water to water needs a difference in temperature. So if I had a system that needed 120 degrees Fahrenheit on a design day to heat it, and now I've put another heat transfer spot between the heat source and the load, well, now I'm running my heat pump even hotter to deliver that 120 on the load side. So that heat exchanger, if you've sized it correctly, is probably going to be pretty expensive. It's going to need a lot of surface area to transfer heat at a fairly low delta T. Plus you're going to need another air separator, another expansion tank, another relief valve, some more makeup water, the list goes on. It may not save you as much money in glycol as you think, but it is going to make your heat pump less efficient every day of its life. So be careful with these systems, select your heat exchangers carefully. Then we have our split heat pumps. So split heat pumps are what we're most familiar with in the air-to-air side of the business. Air source heat pump outside, refrigerant lines bringing that refrigerant into a wall-mounted or floor-mounted indoor unit where it goes refrigerant to water. Sometimes we call that a hydro box depending on the brand. But the wall-hung ones really aren't that unfamiliar to us. It's almost like hanging a boiler on the wall. There's just no venting off of it. So we've got water lines, refrigerant lines, maybe a condensate drain if it's running in chilled cooling. But very easy to integrate into the beautiful mechanical rooms I know you guys like to make. Nice part about this is now the water lines are not outside. Refrigerant's not going to freeze when it's cold out, so we don't have to use glycol in a system like this. This can alleviate some of those issues and challenges with glycol, but now you have an opportunity for mistakes in the refrigeration side. So if you don't have a good fridge tech friend, please get one. They are going to be essential in this, but they're going to have to run those line sets, purge them properly, charge them properly. But this can be a great solution as well. What's nice about the monoblock is you don't have something in the mechanical room, so if you have a tight mechanical room, this might not be the best fit for you. Move some of that equipment outside. On the other side of things, this is going to have a smaller outdoor unit. I don't know any homeowners who say, could you please make that thing outside my house bigger? So splitting all those essential components into two can save some of that mass outside. Now, typical components in these things, we have a fan on the outdoor unit that's going to move that air across that heat exchanger. We have the heat exchanger itself, the compressor. Most of the refrigeration components are going to be in the outdoor section in these split heat pumps. In the indoor unit, you've got the other heat exchanger, refrigerant to water, sometimes a circulator pump, sometimes some electric elements for auxiliary heating. Flow switch, almost always, because proving flow is essential before we run that compressor. And other typical safeties we would think of, relief valves, auto vents, those kind of things in any kind of heat source. And there's also a variation of the split ones that's common where the compressor's on the indoor unit. We've seen this with a Canadian manufacturer that puts the compressor on the indoor unit, so it's just a fan and a heat exchanger outside. Whether that means you're moving noise that's outside to inside is another debate, but nonetheless, they're out there, they're available. Another tool for the tool belt. So glycol. Glycol means that you're going to have to increase your flow rates because glycol transfers less heat than water does. And it means you're going to have to increase the size of your pumps because it's significantly more viscous than water. So you're dealing with higher pressure drops. On top of that, heat pumps want to move more water than we're used to. We've kind of come to this agreement now that forced air systems, if you go to from an oil furnace to an air-to-air heat pump, I hope you're adding duct runs. We've accepted that we're dealing with a little less temperature rise for a higher volume of flow. I don't care if it's CFM or GPM, exact same thing applies in air-to-water heat pumps. We're moving more flow to transfer the same amount of heat, just a shorter temperature rise. That's critical to understand because people get into a habit where I'm hanging a 50,000 BTU boiler on the wall, I can run this in this size piping and use this size pump, and you start talking heat pumps and you start talking glycol, and you are going to have a system that will not last as long as its warranty, unfortunately. So on top of that, you're crippling its capacity, you're crippling its efficiency. Buffer tanks. Buffer tanks are another key ingredient in a successful hydronic heat pump application. When we're dealing with a forced air heating system, we probably aren't zoning it very much. And if we are, it's maybe 2, 3, 4 zones max if it's a central ducted system, so maybe a quarter of the total load. I've seen houses with 60 hydronic zones in them. It's insane. We're dealing with tiny micro loads. The other problem here is the heat pump is so effective when the temperature is mild that there is so much heat energy it's generating when there's almost no load. We are going to short cycle that thing without a way of storing thermal energy. thing about a conveyor belt of heat energy is it's not just putting heat into water. That water has to get rid of that heat somewhere. So you can't just warm up the water. It helps to store it. So think of a buffer tank like a thermal battery. It warms up, heat pump turns off, and that essentially becomes your heat source for the rest of that cycle. So you can now deliver heat to your various different heat emitters from that buffer tank while that heat pump is just taking a break. Then when the buffer tank temperature is dropped by a predefined amount, heat pump comes back on and just warms it back up again. So you get some nice long cycle lengths. I don't know how much you guys know about compressors. They do not like short cycling. Gas appliances don't like it. Electric appliances don't like it. Compressors hate it. So if we can keep them running long, we keep those compressors properly lubricated with oil, we keep the lock rotor amperage draws to a minimum, thermal stress to the wiring to a minimum, and we get a nice efficient system. Buffer tanks are going to be key to that, but buffer tanks create more challenges if we're not used to working with them. I've used them in non-heat pump applications plenty of times, but they are a way of storing energy, but you also have to understand what it's doing to your system. So there's a few different ways to pipe a buffer tank that are pretty important. So this is a 3-port buffer tank configuration where we have our heat source transferring heat into the buffer tank and taking heat from the buffer tank, or fluid from the buffer tank to be reheated. We keep the hottest water at the top, coolest water on the bottom, because that's where they want to hang out. Buoyancy, it's a thing, we can't fight it. Keeps those hot air balloon guys up in the sky, they love their jobs. But on the load side, we're actually taking the water right off that supply of the heat pump before it touches that buffer tank. That's important for low mass heat emitters. We've got all kinds of different heat emitters in hydronics. Your big slabs full of concrete and what we call thermal mass. Thermal mass is all that energy we can charge into that slab and then just let release for a long period of time. Great for limiting cycling on a heat pump, but what if you're using panel radiators? What if you're using staple up underneath the joist space? What if you're using fan coils? Somebody turns up a thermostat because they want to be warm. You want the hot water coming out of that heat pump going straight to that fan coil right away. This is different from a 4-port buffer tank configuration, because in a 4-port buffer tank configuration, you have to warm that tank before you can start transferring heat out to the load. That can be very devastating to a low mass heat emitter system, and even worse to a heat-cool system. Let me talk about some mistakes I learned the hard way. When someone turns on the air conditioning and hot air starts coming out of the fan coil because the buffer tank's still warm, you don't make friends. So some of this stuff is pretty important to understand. We can't just throw tanks in and hope they'll work. Port size is important. Orientation is important. Piping configuration is important. I've got a slide here that's unrelated to everything I've been just saying, but I'm going to talk about it anyway. We heat, we cool, and we defrost with an air source heat pump. So we talk about heating water, chilling water, but anytime we're heating with air as a source, we're going to start freezing up that water on the coil. So the heat pump's going to go into a defrost mode, and it's going to melt off all of that ice and frost on that coil so it can go back to heating mode. If we don't do that, that big block of ice can't transfer heat properly, the fans can't blow air across it anymore. So it's very similar to air conditioning cycle, but the fans stop. We're not trying to pump heat out of the space, we're actually just trying to melt the ice that's right on that coil. But when it does that, there's 2 things to remember. One, that water's got to go somewhere, so hopefully it's not running across a pathway and refreezing, creating a slipping hazard. So think about that when you place your heat pump. But also things like as it reaches the end of a defrost cycle, some of that water is going to vaporize, turn into steam. I have more stories than I have fingers to count them on of homeowners thinking their heat pump is on fire and calling the fire department. So make sure that you're talking to your clients about this. Tell them this is normal. It's something to understand that is going to happen. In fact, the more efficient the heat pump, probably the quicker it's going to frost up. It's a good thing. Look at how good a job it's doing of taking heat out of that air. It froze. It's great. It's not a bad thing. Just hopefully it does it quickly. So it looks like that. You know, you might not have snow on the ground, but you got ice on the heat pump. Hopefully it terminates quick. There's a few different modes for that. Try not to do some things. You know, sometimes you gotta poke some fun. So air source heat pumps get their heat from the outside air or reject their heat to the outside air. So make sure it's fresh air all the time. Don't put it in a confined space where it's gonna recycle the same air over and over again. You're just gonna start going down a rabbit hole you'll never come back out of. You want to avoid having one heat pump blowing its air into another heat pump because you've already taken heat out of that air. That next one's going to have a tougher job. You want to make sure that you avoid placing these things where they're going to get snow landing on them, or if they're cooling the house, you don't want a hot air vent pointing at them. But a real key thing is to make sure there's no obstruction in front of the discharge, whether that's a side discharge heat pump or a top discharge heat pump, free and clear of anything that's going to impede airflow. So, you know, they're kind of unsightly, but don't put a decorative rock in front of it. That's a side discharge heat pump. That thing has no chance of doing its job. You want to protect it from snow, but I don't know any fridge mechanics that are going to be able to get at the compressor on that thing. So maybe it needs some hinges. The air is going to come out of that, but I don't know how it's getting into the backside of that coil. That would not be a heat pump that I'd say has free area in front of it. Those stairs exist, and they're probably going to be pretty icy at certain times of the year too. So try to avoid something like that. Putting these things by dryer vents, probably not a great idea. No knock at this particular heat pump, it didn't stand a chance. Covered in dryer lint, that was once a blanket, it is again a blanket, affecting our ability to transfer heat. So cleaning these things is important. Leaves, grass, snow, whatever it is. So side discharge heat pumps are pretty popular these days. You can tuck it up closer to the house. It tends to direct the noise in the direction of the airflow, so towards the neighbor and not your bedroom. We also have top discharge heat pumps, which are also great. You know, send that air straight up. Maybe it can be closer to a fence or a side yard if you're allowed to do that. None of these things are vastly different from each other. They're just orientations I want to familiarize you with. But you do want to minimize your pipe lengths, whether it's hydronic piping or refrigeration piping, the bends in that. You want to make sure these things are above the anticipated snow line so they're not just buried in a drift of snow. And you want to leave them access for service. I'm sorry, not every service tech is as svelte as I am, so you need to plan for that guy that needs to crouch next to it and get that compressor out of there. Also want to maybe protect it from frost or a sea spray off the ocean. There's some great waterfront properties around here. That salt air is not so great for fan rotors and fins and all these other fun things, so maybe protect it from that. I've seen some heat pumps with beautiful water views, but unfortunately they didn't last. So this is a monoblock heat pump, air source sitting outside somebody's very nice house, up elevated above the snow line. There's some insulated and cladded water piping going into the mechanical room. Cladding helps keep the birds out of it. You want to avoid noise disturbance, so don't put this thing right outside the primary bedroom. Maybe put it somewhere that no one's going to really notice. They are not silent. They're getting better, but they're not silent. Choose a quiet product. You know, if you're trying to keep it quiet, start quiet. Thing about noise is it doesn't get any quieter than at the source. So pretty typical to need somewhere around 5, even 6 feet off the front of a side discharge heat pump or off the top of a top discharge heat pump. So top discharge heat pump under a deck, not a great idea. But that could maybe live under a deck, rejecting heat out to the outside or absorbing heat from the outside. Try not to put these things right in front of the front door. I don't know if you like the people that canvass your neighborhood, but if it's a cold day, it's even colder air coming off of that heat pump. It's not a warm greeting to your friends and family. And we have penetrations through the building we need to seal. Slope them towards the outside. Make sure they're airtight. Make sure that they're watertight. There's all kinds of accessories out there for this industry to make sure that these things are done cleanly and nicely. Don't just drill a hole and slam some pipe through it, please. There's some great products out there to clean this up, or just some common sense. Now, let's talk about thermal performance, some things that affect the efficiency of a heat pump. Outdoor air temperature, huge one for an air source heat pump. That's where we're getting our heat energy. So the warmer it is, the more heat energy there is in that, which really makes pinning down the efficiency of a heat pump like a dart on a wall. You can't pin it because it's a momentary measurement. Our load side water supply temperature. So the more temperature lift we're trying to get from the heat pump, the harder it has to work, the less efficient, and the less capacity. So what comes out of this, I already see a lot of people doing great low temperature hydronic heat emitter designs because condensing boilers work great at lower return temperatures. That's how we condense those flue gases, another latent heat exchange. But with heat pumps, there's an even more drastic efficiency change with leaving water temperature. And things like adding antifreeze. Try not to use more than you need. Try not to use bigger circulators than you need. Just typical things that are all going to lead to the difference between a system that's very effective and very serviceable to something that looked cool on paper but just slugs through energy like no one's business. So COP, I already covered this. Wattage out, wattage in. We get more out than we put in. Good job, everybody. So COP is how we measure these things. You can measure it quite easily. If you know what's coming out of that hydronic system through temperature difference and flow rate, you can calculate BTUs. You now know how much you're delivering. Simple to do with a couple thermometers or even some PT ports and some gauges you bring yourself. Now you've got your delta T. If you've got a pump curve and a couple pressure gauges, you can use that to calculate your flow rate. So you now know what you're delivering. Grab your amp meter, put it on the compressor, grab your voltmeter, measure the ingoing voltage, and now you can figure out how much energy is being consumed. You right there with a couple gauges and one relatively inexpensive multimeter can now calculate the efficiency of these things. So it's great to do when you install them to set a benchmark. Make sure you haven't missed something, but also know how it was performing when you left it, so when you come back to check on it, you know if things have varied. It's also a good point to figure out if you do need to change a balancing valve or change a pump speed or something like that. Something about air source heat pumps that I hear a lot of people talk about is, oh, they suck in the winter. They just don't do a good job. A lot of people, especially in the forced air industry, use gas or electric as a backup, and when that comes in a lot of cases, the heat pump turns off completely. It no longer has enough capacity to heat the house, so off it goes, on comes the backup, and up goes the hydro bill. So what's nice about hydronics is we can use them in conjunction. But I want to point out just how little of the year we operate at design conditions. We're standing here in the greater Vancouver area. This is some bin temperature data from the city of Vancouver. Bin temperature data is basically saying how many hours in a year do we spend in a certain bin or range of outdoor temperatures. So we drop these into 5-degree ranges or bins, and well, on average 3 hours a year at design conditions. Meanwhile, the bulk of our run hours are right in that middle, right where we're dealing with partial load conditions where these heat pump efficiencies are much, much higher. So we need to make sure we cover the design load, but we don't necessarily have to do that with a 100% heat pump. We can do that with a heat pump that covers most of the partial load conditions and use something less efficient like electric resistance as the added capacity for those coldest days, because they're brief. At our design temperature, when we're 100% of design, that's 0.03% of the actual heating season, so 3 hours roughly. Meanwhile, 32% to 67% of the load, these three sections here, represent a large chunk of the heating season. So just remember that when you're selecting your heat pumps. You don't have to find a heat pump that's going to cover 100% of that design load. If you do, you're probably going to end up with a pretty big buffer tank if you did your math right as well. Now, our efficiency goes up as the outdoor air temperature goes up. Great thing, we've got more heat energy there. It also goes up as the leaving water temperature goes down. So if I can heat with lower temperatures, I gain more efficiency with that too. So if you guys aren't familiar with a concept called outdoor reset, it's a huge benefit with hydronic heat pumps. As it gets milder out, we can heat with lower and lower temperatures, and that's got a doubling effect because not only is the heat pump working more efficiently because it's warmer out, it can operate more efficiently at those lower temperatures we can still heat with. And then flow rate also affects efficiency. Not by as much, but it's still important. The big thing with flow rate is if you don't have enough, you're going to start damaging your heat pump. Overpressurize the refrigeration circuit or low suction pressure when you're cooling. So a couple of slides illustrating some of the differences in efficiency just by changing the leaving water temperature. Right here on the right, I've got outdoor temperature left to right from cold to warm. On the left-hand axis here we have COP, so higher on the scale, more efficient. Got two lines here, a blue one and a red one. The blue one is a 95-degree leaving water temperature in Fahrenheit, and the red one's 130. So 130 is not that hot in the scheme of hydronics, but there is a massive change in efficiency just by dropping 40 degrees on your leaving water temperature. Do that all the way across the heating season, and there's some significant advantages to low temperature hydronic heat emitter design. Let's talk flow rates. 2.5 to 3 gallons a minute per ton is typically what you're going to see. Now, ultimately, check with the manufacturer specs for the heat pump you're looking for, but this is 2.5 to 3 gallons per minute per ton. So if you're doing the math, that's 2 to 3 times the flow you're used to for gas and electric boilers. Bigger pipes, bigger pumps, plan for it. If you don't have that kind of flow through it, especially with inverter heat pumps, they're going to protect themselves and ramp down and never even run to full capacity. Inadequate water flow has a detrimental effect, and of course we can ultimately just destroy the equipment if we run it with too low of water flow for too long. So let's talk buffer tanks again for a minute. This is a 4-port buffer tank. The 4-port buffer tank method is very popular. It's very easy to achieve hydraulic separation. For those that don't know what hydraulic separation is, it's a way of combining two separate circuits in a hydronic system so they don't influence flow within each other. So a change in flow on my load side does not represent any change in pressure drop on my source side, which means my flow rate stays consistent no matter what's happening on the load side. You can do this with closely spaced tees. You can do it with low loss headers. You can also do it with 4-port buffer tanks. Buffer tanks have very little pressure drop because it's a very low velocity through them. Great big chamber, low flow rate comparatively. So that acts like a low loss header. On this side we have our primary circuit where our heat source is just interacting with the buffer tank, and on the load side we've got our secondary circuit drawing heat away from the buffer tank. As far as we're concerned, after that buffer tank, everything is back to normal. Keep it low temperature, but you don't have to change how you're dealing with flow rates and things. It's just on the primary loop that you need to deal with these higher flow rates. So normal design parameters, higher flow rates than your typical boilers. If we do primary, secondary piping, we're going to have some successful systems because we can make sure those heat pumps get the flow they want. Some of the most challenging, I'll nicely say, air-to-water heat pump systems I've been involved with were ones that were direct piped, where we were trying to get the kind of flow rates through the heat pump that they needed through the entire system. It wasn't designed for that. We're used to, 10 or 20 degree delta T's in our radiant floor panels and things like that. We're dealing with like 3 to 9 degree delta T's on our heat pumps here. We're just not sizing our heat emitters that way. We're not sizing our pipes that way, and we don't have to. We can still transfer the same amount of heat from one circuit to the other. High flow, low delta T meets low flow, high delta T. BTUs still transfer. So decoupling it, very important. 4-port buffer tank, very easy way to achieve hydraulic separation. So very popular for that reason. But like I say, that buffer tank is interacting with the load at all times. So if this thing has been turned off while I was away vacationing and I come home and I turn on my heating system, all that water has to be warmed before any of that heated water gets out to those heat emitters to start heating the house, which slows the system down. If we're dealing with a thick floor slab that takes 8 hours to respond anyway, no one's going to notice. But like I say, if that's a fan coil, a panel rad, they are going to notice. That's where we use things like 3-port and 2-port buffer tank strategies. Now let's just get right down to it. I picked 2 products on the market. I may or may not sell them. That's not why they're there. The point is, one is a gas boiler and one is an air-to-water heat pump. And they're about the same capacity. So around 50,000 BTUs. On the left we've got a heat pump. It goes anywhere from 8,600 BTUs to almost 75,000. Now that's not at the times when I need that 75,000. That's at the time that I don't know what to do with that 75,000, when it's mild out. But it's rated at 52,886 with an 86 degree leaving water temperature when it's 23 Fahrenheit outside. So we can only really pick a set of numbers to give it a number, but that's the range. Meanwhile, we've got a gas boiler that gives us between 8,000 and 55,000 regardless of the weather. So we need to start thinking about things like balance point charts when we're sizing our equipment. I've got some slides to show you what that means. We really need to understand the relationship between the heat source and the load as the outdoor temperature changes. A couple other distinctions here. Well, that air-to-water heat pump can cool. The boiler cannot, so that's a thing. Flow rate, 15.4 gallons per minute. That's a 6.9 degree delta T. What's the boiler want? 5.1. Same BTUs, 50,000 BTUs roughly each of these appliances. So if you were sizing that for a 20 degree delta T with 100% water, that could be a 3/4 copper pipe. The other one's going to need 1.25 inch minimum. Those are minimum sizes. We haven't even started adding glycol or distance. So that right there is the first step in properly applying these products. Let's take a look at pressure drop. This is a water tube boiler, so pretty high pressure drop in the boiler world. 7.4 feet ahead at that 5 gallons a minute. 23 feet ahead through that heat pump. Now we are moving more flow, but we are going to be using a larger pump for this than that other boiler. Operating temperature range. In heating mode, this thing can create heat anywhere from -4 Fahrenheit to 95 Fahrenheit outside. The boiler doesn't care. Something else to think about. I know it doesn't get above 95 that often, but if you want to do domestic hot water off of your air-to-water heat pump and you live somewhere where that's going to be a problem, you're going to need to plan for some summer domestic hot water. Or if you're doing chilled water cooling with your system, you're going to need to figure out which one's going to take priority in summer, because trust me, people that don't have hot water and don't have air conditioning when they need it are the most irate customer you can deal with. Lastly, supply temperature range. Both start at about 77 Fahrenheit. We can do a lot of heating at 77 Fahrenheit in hydronics. The boiler, all the way up to 194. Great job. If it's actually boiling, you're doing it wrong. Forget the name. But the heat pump, 131, max, downhill with a tailwind. It does not get any hotter than that. That's based on R410A, and that's just a limitation of that. So this has a real hard line in the sand of where it can work and where it can't. You're dealing with an atmospheric boiler and some fin tube baseboard that needs a high delta T to get that convector convecting heat. That heat pump is not a good fit to that. You are going to have more baseboard in that space than you are comfortable with to make that effective. So you're either adding more surface area to your heat emitters to get them to low temperatures, or you're stuck in the electric boiler world, unfortunately. But there are some real limits there. And at 131, we have lost a lot of capacity and a lot of efficiency. So don't design for those maximums. Be aware of the maximums. Design even lower, because if that's a monoblock, that's 131 leaving the unit outside on a cold day. Are you getting 131 into your floor? Probably not. So, and that's at its least efficient. Glycol, I already kind of talked about this stuff, so I'll skim over that. But turns out water freezes without it. So something else to note is chilled water cooling. I talked about monoblocks, I talked about splits. Somewhere you're going to use glycol in both applications is chilled water cooling. The temperature inside that heat exchanger is cooler than your leaving water temperature, and all it takes is a pump to decide, you know what, today was my last good day of service, and suddenly the water in that heat exchanger freezes. That heat exchanger's toast, probably the compressor too. That is a very expensive bill. Add some glycol, you're protected. So any chilled water cooling application should be using glycol as well. How do we test glycol? Refractometer. It's kind of like a pirate telescope. It's really cool. Act like a science teacher or something, drop a little sample of fluid on the glass, close it, point it to a light source. You see something like this. It literally tells you the percentage of glycol. It couldn't be an easier tool to work with. Pick one up. If you're working with glycol, you'll know how much you have, and you can verify the concentration. Glycol has freezing points and bursting points. When you're selecting your glycol, bursting is not the one you're looking at. It is freezing. Once the water is frozen, it doesn't move around very well. I don't care that the pipe didn't break. We can't transfer heat through a slushy. So look at the freeze protection numbers, and you're usually going to be in that 20 to 30% range depending on where you're installing it, but less is more. Make sure you're protected for the application, but don't just throw as much glycol as you can in there because there's a massive effect on pressure drop and flow rate, as I mentioned before. How much? Well, here's a correction factor slide of flow rates. So roughly at, let's call it 30% glycol by volume, and let's call it 100 degree Fahrenheit water, we now only transfer 95% of the heat at the same flow rate as we would have if it was 100% water. So we're going to need to increase our flow rate, our design flow rate, to still get that 100% goal we had. 5% is not a lot. Pressure drop is a much bigger one. That same 20% blended glycol at a 55 degree temperature outside is about 30% more pressure drop than 100% water. So again, you're going to want to make sure you're following these charts and going through to make sure your pump has been selected for these parameters, and your heat pump's going to get the flow it needs to have a nice long life. An important thing to know about sizing glycol is how much fluid is in the system. So you're going to need to add it all up. I'm sorry, there's some software that can make it easier, or that's what they made apprentices for. Count up all the piping in the system, figure out how big it is, figure out how much volume's in there, and it's just a percentage of that. You don't usually buy glycol in 100% format, so then you apply the percentage that you're buying it in to figure out how much you need to buy. Usually it's 95% or 50-50. I try to buy more glycol than water because I don't like shipping water in buckets and paying someone to do that, but you never buy it 100%. So we've got some formulas in our workbook to figure out exactly how much glycol you're going to need to buy from your supplier. So what happens if we don't have enough water flow? As I mentioned before, when we're in heating mode, pressures go up in the refrigeration circuit. We can't dissipate that heat. Things climb and climb. Things shut down to protect themselves. When it's cooling, our suction pressure starts dropping and dropping. Again, bad thing. We want to make sure we have ample flow through these systems. Now let's talk about heat emitters. Radiant floor, great, popular. How about cast iron radiators? That was a brand new place in Oak Bay, Victoria that got these fancy refurbished radiators. If you get enough of these together, you can very effectively heat at low temperatures. It's just a surface area versus delta T equation again. So this radiator here is going to give you 50 BTU a square foot with 120 degree average water temperature. But if we were running that at 185, it'd give us 180 BTU a square foot. So size them based on the water temperature you're working with. You can do that with cast iron rads, you can do that with panel rads. They work great. On top of that, we've got some fan coils on the market. You might say, hey, that looks like a ductless mini split. It kind of does, but it's hot or cold water running through it. So this would be a great way to retrofit some cooling into an existing radiant floor system. Toss something like that up in the primary bedroom, and now you've got some summer cooling out of that heat pump that otherwise was just sitting there until it became heating season again. We want to use fan coils to cool because they have drain pans. Big part of human comfort when we are cooling is dehumidifying. If we're too warm, we sweat. Sweat doesn't work so well when the air is wet, so we need to drop that humidity to be comfortable. We can be comfortable at a higher temperature if the humidity is lower. If we're just doing radiant cooling, that is running chilled water through the floor, there's some limits to how much cooling we can do based on the dew point. The dew point gets calculated by surface temperature and humidity, and we can control one of those. And the other one, well, we live in a rainforest. We can't control this. You know how long it takes a slab to change its temperature? So picture a nice hot day, you're running chilled water in the floor, everything is great in that house, and then everyone comes back from the beach. Doors go open, wet stuff comes in, dew point changes. There's some great controls made by some great people in the back of the room that can manage this, but they're going to turn off your cooling when it gets moist in the house. I would rather just put a drain pan in there, plan for it. So ductless or ducted fan coils exist. They come in lots of different flavors, slim duct, central duct, whatever your format you prefer. Pipe it to drain, get rid of that latent heat. You'll have a much happier system. You can use some radiant floor in conjunction with forced air chilled water cooling to try and cut down on some of that sensible load and do it with the efficiency of hydronics, but you're going to need some air movement anyway. This would be my advice. Go with a fan coil for chilled water cooling. Now that fan coil could also be used for some heating. So maybe the top floor of the house is a fan coil, bottom is radiant floor, or maybe you have one heat emitter that does one thing and the other is strictly cooling. That's okay too. Lots of ways to control these things and pipe these things. Then we've got baseboard. I already made a bit of an enemy with baseboard earlier tonight, but there is some low temperature baseboard on the market. Just bigger fins, more pipes to get more heat with lower temperatures. That's really the goal with these systems. Got panel radiators, great way to retrofit an existing system, snake some oxypex through an existing space, pop it up, put a rad up, hey, now you got some heat somewhere you didn't have. So these things are great. Don't run chilled water through a steel panel radiator, but great low mass heat emitter. Let's talk about radiant floor for a minute. They're not all the same. We've got our high mass wet stuff in concrete, then we've got our retrofit under the floor stuff, or maybe the don't have the structural support for concrete type of stuff. There's good, there's bad, and there's ugly here. Let's start with the good. Something that has some help for heat transfer. A pipe with some aluminum or steel being used to wick heat away from that tube, transfer heat around a bigger space, get lots of surface area between what's coming through that pipe and the subfloor. Because remember, we're trying to heat what's above this floor, not down here. So heat transfer plates come from all kinds of different places. Great way to lower your leaving water temperature on a system like this. If we pop over to the left here, this is just a couple of pipes nailed up with tube talents. So for those of you who are billiards folks, you probably know just how much contact a round surface has with a flat surface. There's, very little conduction happening there. We're just hoping to heat up a pocket of air, and hopefully that's going to heat up the floor enough to hopefully heat the space. You're going to need higher water temperatures with a system like that, and ultimately that's going to affect your heat pump's performance. Let's get to the ugly. I don't know why we do that, but I've seen it. I even had one guy tell me he patented the double helix method of doing that, of twisting it down. He was very proud of it, but that is a thermally constipated system. It is not going to transfer heat into that space above very well without some crazy hot temperatures that we just can't get from that heat pump. Not today. Hopefully we get some more technology soon that can fix that. Got some slides from some nice PEX people here comparing just tubing in the subfloor versus tubing with heat transfer plates in the subfloor. Exact same situation, our 0.5 floor covering. Let's take a look at without plates. I can get maybe 16, 18 BTU a square foot out of that if my water temperature is 60 degrees above my room temperature. That's pretty extreme. Pop over to the heat transfer plates. I can drop that down to a 55 degree delta T and get 20 BTU a square foot out of it. So lowering that water temperature or increasing your heat output, however you want to look at it, these things have a great place in these kind of systems. So make sure you're sizing a system based on that water temperature. The capacity of the heat pump changes as the water temperature changes. So you start with a heat loss calculation, figure out what you have in room by room loads, figure out how you're going to address those with your heat emitters and what water temperature they're going to need, and then you can start to pick your heat pump because the capacity of that heat pump is going to change based on that water temperature. So heated slabs with low resistance floor coverings are great. Thin slabs are great. Lots of different things. We've covered a lot of these already. So some typical temperature ranges for radiant heat emitters. There's lots of different ways to look at this. This is not an end-all be-all chart, just a range. You've got your radiant in-floor working in the 75 to 120 range typically, not much more than that, or I've seen some very expensive marble floors cracked by too hot of water. But even at 75 degrees, barely above room temperature, we can heat a space with radiant floor heating. Radiant underfloor, it's going to start a little higher. but still going to max out somewhere around 120. Great application. We've got our radiant walls and ceilings. Great way to increase some surface area in a space if you're limited by cabinets or stairs or other things in a room. Got radiant panels, cast iron radiators, but some of these things need some pretty hot temperatures. So let's just draw a line. Nothing to the right is going to be a good fit. Everything to the left, going to be a good fit. Try to size it for the lowest temperature possible. So if we're talking radiant floor heating, more pipe. I don't sell pipe. There are some nice people here who do. This is not a pitch for pipe, but it's the cheapest thing in the whole system. Put more in and you can increase those surface temperatures with the same water temperature. Or, to say another way, lower that water temperature to get the same output. To the left, pretty typical standard practice, 12-inch on center spacing. Got our PECs, we've got this stripe of no heat, and then PECs. All these circles represent various different concentrations of heat coming off of that pipe. To the right, we've got 6-inch on center spacing. You'll notice it's not as cold right here. That means our average surface temperature is higher over here than over here without changing the water temperature. Heat output of a radiant panel is based on that average surface temperature. So tighten up that spacing, it'll save you a lot of headaches later. Try to avoid shag carpet and other things that are going to impede heat transfer. Let's take a look. This is a heat pump. Actually, it's not. It's a chart. It's a fixed capacity that is an on-off scroll compressor of a monoblock heat pump. So not super advanced technology, but a good product. Happens to have a lot of data points. It happens to be rated at 57,598 BTUs when it's delivering 45 Celsius water. And it's 7 degrees outside, okay? But all these other data points around here are different than that. I've drilled that point home already. But let's say we take that heat pump and put it into a house. We've got a bin temperature chart, we already covered that. So let's start figuring out how we heat that space. Let's say it's 50,000 BTUs, 2,500 square feet. We can look at all these different temperature bins and figure out just how many BTUs we're going to need for each one of those bins. And we can pop over to a heat output chart for radiant floors, and we can see for each one of those bins, what water temperature do I need? So now, bin 1, the coldest time, our design load, needs 92 degree water. Meanwhile, bin 4, not the burger joint, only needs 83 degree water. So that's where our outdoor reset control strategy really shines. We're getting more capacity from the heat pump, more efficiency from the heat pump, just by dropping that leaving water temperature. So then we can go to this heat pump chart, take a look at each one of those bins. How much capacity do I have at that outdoor temperature and that corresponding leaving water temperature? And we can start plunking some numbers in. Look at this. 32% of the year, I've got 520% efficiency because I only need 93 degree water to heat that space because it's a 50% of the design load. 29% of the year, 545% efficient. Huge, huge numbers, much better than what's on the rating plate, certainly better than the number on the design condition, but these are the largest parts of the year. So you could then take that by the number of hours, start running some numbers on what you pay for hydro, and you can start figuring out what this is going to cost to operate. Without those steps, you're just sort of blindly hoping that this thing is going to work, but a big chunk of that year, a big part of it is partial load conditions. Outdoor reset, air source heat pumps, great friends. So what's the break-even point? Everybody loves this question. Natural gas versus electricity. You know, today on step 2 and what we're paying for gas, COP of 6 is probably going to be that break-even with a 90% combustion efficiency appliance. Step 1, going to be more like a COP of 4. But that is going to change. Our electric rates are going to change, our gas rates are going to change, technology is going to get better. This is just the break-even point against what's said to be the cheapest way to heat right now. Compared to oil, compared to propane, compared to an electric boiler, this is going to save money quick. And it's going to save money as those gas rates go up and up as they get taxed more and more. Last thing I want to talk about, because I know I've already gotten the time window and I'm still talking, balance point calculations. I mentioned this before. Key part of any air source heat pump system. I just want to take you through it. Along the bottom of this I have outdoor temperature. On the left side is capacity. Here's a slide version of the output of a heat pump. The black line is the nominal load. Each one of these lines represents a different leaving water temperature and its capacity at different outdoor temperatures. So I can take a design heat loss right here, and I can say I need almost 60,000 BTUs at 19 degrees. So that's what the house needs, and as it gets warmer out, it needs less and less heat. Meanwhile, this is my heat pump. I get lots of capacity over here and less and less and less as the temperature drops. This blue line represents the balance point. That's the outdoor temperature where 100% of the heat loss can be met by the heat pump running at 100% capacity. Any warmer day outside than that, we can rely on 100% heat pump. Colder than that, we're going to need some help. How much? Connect the lines. There's our load. That's how much I get from my heat pump. The green line is how much I'm short. Throw that in as an electric element or an electric boiler. You've covered your design load. Meanwhile, you've got all this excess capacity from the heat pump the rest of the time. And I'm just talking about the whole house. I haven't even started talking about zoning. So this slide is also pretty important on why we need buffer tanks. Right here on this 59-degree day, look at how much heat my heat pump wants to give me, and look at what the house can take if every single zone is open. That's why we need buffer tanks in these systems, to prevent short cycling. We've got formulas to size them based on temperature difference in the tank, based on minimum zone load. Happy to go through all that in detail at a time when I've been given more time. But nonetheless, they look like this. It's a tank. There's lots of them on the market. They're insulated, but if you're running chilled water through it, make sure it has some vapor-sealed insulation. We don't want that tank to start sweating with the chilled water in it. It's going to rust. It's going to fail. I've seen them die in less than 2 years. So make sure you're picking the right kind of buffer tank if you're doing heating and cooling with these systems. So there's a lot of different ways to preheat domestic hot water and top it up with another heat source when we're dealing with hydronics. We spell all that out in the course and in our piping handbook. Looks something like this. If you've seen a hydronic piping diagram from TECA before, not much different. This is a split air-to-water heat pump. And this is what the load piping might look like. This would be a fan coil and radiant floor heating off a 4-port buffer tank. So we've got a whole library of these kind of drawings coming out, different configurations, diverting to a fan coil for cooling, radiant floor heating, fan coil and radiant off a 3-port buffer tank. We've got heat-cooled buffer tanks and multi-fan coils and backup boilers, and it's real fun stuff if you're into this. So just a taste of what's coming out soon. We've got so many drawings, it's kind of absurd. I want to thank you guys for your attention and your time. I hope you enjoyed dinner tonight. Have a great evening.